section 6.7, we can also calculate the mass percent composition from the chemical formula. Not doing an experiment, but just looking at the formula. And again, it's that same idea. The percent of a given element is going to be the mass of that element divided by the mass of the entire compound. What's convenient to do here, since you have no specific mass of a sample, is to say the mass of element X in 1 mole of the compound divided by the mass of 1 mole of the compound times 100%. And there's the percent symbol. So calculate the mass percent of fluorine in C2Cl4F2, which is also known as Freon 114. There's a whole bunch of different freons. So the percent fluorine is going to equal the grams of fluorine in 1 mole divided by the grams of C2Cl4F2 in 1 mole times 100%. So we need molar masses. We need a periodic table. So in that formula, how many moles of fluorine are there in 1 mole of that compound? 2, because it's F2. So every molecule has 2 fluorine atoms. Every mole of molecules has 2 mole of fluorine atoms. So then in the numerator we have 2 times the mass of fluorine. 19.00. Oh my goodness. Then the bottom one, we just calculate the molar mass of that compound. So that's 2 times the mass of carbon plus 4 times the mass of chlorine plus 2 times the mass of fluorine times 100. Now, can you string that all together in your calculator? You can. A lot of times those students end up with weird things when they do that. Someone end up with like 8,000% because of order of operations. So this is one of the few instances where I will say, maybe it's better to figure out the 2 numbers separately. 38.00 grams. And on the bottom, 203.82. Anybody else get that number? Thank you. And we end up, because of the molar masses we used, we can have 4 significant figures. 18.64% fluorine. So in 100 grams of that compound, there's 18.64 grams of fluorine. That's what the percent composition means. You can calculate if they don't specify the percent composition of fluorine, then they want you to calculate the percent composition of every element. And in that percentage worksheet, they make you do that on the first one. They want all the elements. As a check, all those percentages should add up to 100 or really close. You might end up with like 100.1 from rounding issues. So any questions about this sort of a calculation? This ends up, we see this, what? Stay. In lab, we end up with things let's see. I don't know. We sometimes do experiments where we deal with hydrates, and I believe we did one of these. I don't remember for sure. But there's a question like it on your worksheet. And they'll ask you what the percent water is. Not the percent of an element, but the percent of the water. And so then you need to find the mass of water and divide by the mass of the whole thing. So there are 5 water molecules in every formula unit of this. And so you're going to have 5 times the mass of water, which, I just happen to remember because I do it so many times, divided by the mass of the copper sulfate. And I'm pretty sure this is one of the problems, so I'm not going to do the whole thing for you. But down here, you need the molar mass of that whole compound, CuSO4.5H2O. So you can calculate that. So the percent water, instead of it being interested in hydrogen or oxygen or something separately, we're interested in the water content. Okay, so you find the mass of the water, and you have to consider that number in front of it. Okay, that tells us how much water is in there. Okay, any questions?
So that's for all of the problems that say hydrate?
Anytime they're asking for percent water, this is how you would calculate a theoretical percent water. Experimentally, which I think the next question, if I remember correctly, I just wrote the key for that, so I'll just make up some numbers. Say you took 5.00 grams of hydrate and you heated it, and then all the water evaporates and goes away. And let's say you've got 2 grams of anhydrate. What does the prefix "an" mean? It means without. The hydrate has water associated with it. The anhydrate does not have water. That's the dry, just the plain ionic compound. And a hydrate is different than something that's just wet. So this would be experimental data. You weigh the hydrate, you heat it, you weigh it again, it weighs less because the water went away. To find the percent water in this compound, we need the mass of the water divided by the mass of the hydrate, the whole thing, times 100%. How do we find the mass of the water? Yeah, we'll subtract the 2 grams from the 5 grams. And sometimes it's helpful to look at those, you've got all the data, and look at these and say, well, what's the difference between this one and this one? What's different about it? The water went away. The masses are different. If the difference is the water went away, then maybe the difference in mass is the mass of the water that went away. Okay? This finding out masses by difference is confusing for a lot of students. But it shouldn't be. Okay? It shouldn't be. And so I think some of us have a little, you just assume that anything chemistry related has to be too hard. And yet if I ask you to figure out how to weigh a squirmy puppy dog, you can figure that out, right? You get on the bathroom scale and you make a note of how much you weigh. Then you pick up the puppy and you get on the scale again. Now you weigh more because you're holding the puppy. The difference in mass is the mass of the puppy. You didn't weigh the puppy directly. There's a lot of times in science where we can't measure things directly, but we can measure before and after and figure out the difference. Okay?